Welcome. This is the bonus seminar of the Exploring Our World activity that's part of the PNG and Australian Partnership of Secondary Schools. My name is John Bailey, and I am the person that created this activity and has been leading these seminars. Now, this is just a recorded seminar, as in it's just me talking to myself, but I've been teaching high school for the last few months, so this is something I'm very used to. So in today's seminar, we will be going through chapter 5 of the student workbook and looking at some things that are a little bit different compared to the other chapters. The other chapters were focused on the use of Google Earth and how we can use Google Earth as a storytelling and an exploration tool. And we were looking at the different functions and features and content in there, as opposed to this seminar and this chapter, where we really get into the physics and the science behind the key part of Google Earth, which is, of course, those images that make up this mirror world, this model world that we're able to explore. And so we'll be covering a number of topics to do with image resolution, what shapes and colors mean in satellite images, and even how we can view beyond the visible range, how we can use sensors on satellites to detect things that we can't see with our own eyes. But just a quick reminder, this is the core of this activity, this module, Google Earth. You can explore it here. And again, today is more about the science of remote sensing images. So we might see a few examples where we've used Google Earth, but we're not fundamentally going to talk about functionality in Google Earth. However, we are going to start there with an image from there, typical sort of urban landscape, because one of the things we haven't really mentioned in Google Earth is the most important thing, the thing that everyone wants to use it for, which is, of course, finding their house. This used to be my house some time ago. I don't live there anymore, but this idea of finding our house seems kind of silly, but you know what? It's actually a good thing. Think back just how few years ago people had ever seen their house, their town, even their country from this perspective. With the evolution of tools like Google Earth and maps that you can view on your phone and these types of technologies, it's opened up a view of our planet that we've never truly had before. At least only a few of us really had it before. And so if this is a way to introduce people to the idea of using satellites to look at the planet and understand the changes going on, then that's great. But what are satellite images? Well, put simply, they're a visual representation of digital data that is captured by sensors on a spacecraft orbiting a planet. Basically, big camera in sky looks down on planet. Of course, it's a little more complicated than that. And we have a name for this process. It's called remote sensing. Now, that might sound very complex, but remote sensing is something we all do. You know, we do it every day. Our senses, our sight, our smell, our ability to hear, these are forms of remote sensing. We are some distance away from the target that is smelling or that we're hearing or that we're seeing, and we're using those sensors in our body to detect information about that target. And this is really no different to what satellites do above the Earth, detecting information and turning it into graphical representations ultimately that we can view. But before we get into that, let's do a little sort of quick history of where this remote sensing of images came from. And I guess really the place to start is photography. This is generally credited as the world's oldest known surviving photograph, taken by a French gentleman at the start of the 19th century. And here he had a metal plate coated in chemical that was exposed to light for a long period of time. and he gets this shadowing effect, which captured the image that was in front of it. Now, this photography stuff obviously took off and evolved over the years and decades and centuries. Kind of one of my favorite stops along its evolution occurred at the start of the 20th century, where now we had, you know, quite mobile cameras, really, if you think about this over 100 years ago technology. But they started thinking about ways to capture these images, not just from that ground perspective, but what you might see from the air. So they put these cameras on pigeons, something they did during World War I as a way of trying to produce reconnaissance of enemy territory. I think with mixed success. I'm not sure if they got lots of images from the cameras or just the pigeons provided good food for soldiers. But either way, this idea of aerial photography evolved, obviously, as aeroplanes came along. And before this, we already had hot air balloons. But then the real jump is, of course, going into space. And the idea that we can have these satellites orbiting around the Earth, taking pictures of the Earth. And this is really credited as the first satellite-based technology, the TIROS, the television infrared observation satellites. You know, we look at this today and find it almost funny in terms of the quality, but you know, capturing this in 1960 was truly groundbreaking. And this actually, the motivation behind this was they were trying to see weather patterns. And this was a program that continued all the way into the start of the 2000s with the NOAA satellites, which have since been replaced by other satellites. But it highlights that there are certain fundamental things that we really can only do from a spaceborne platform. And one of those is seeing cloud patterns, seeing weather patterns on a global scale. Skip one, next one. Next kind of evolutionary step is the Landsat program. First launched in 1972. This is the longest serving continuous Earth observation program. It's still going now, 50 years later, where there's still Landsat capturing images. It's been a collaboration over the years between NASA and the US Geological Survey. And because we've captured images for so long, it's really a remarkable record of change, because we've got these 5 decades and we can see how the Earth has evolved over that time. But for our purposes, in terms of Google Earth and this world where we can see images, you know, on our phone and down to great detail, the next big jump happened at the end of the 90s, sort of 99 to 2001, with the launch of Iconus and QuickBirds, the first high-resolution commercial satellites, as in anyone could go and purchase these images. And I remember first seeing these images. I was a new graduate student who was using satellite images to study volcanic landscapes. And I'd been using satellite and something called Spot. They were great images. But when I saw this stuff, it blew my mind. The idea that you could pick out things like baggage carts. I think we're looking at Frankfurt Airport here, which was possibly the first place I ever saw one of these high resolution images of. So with this imagery available, it brought in a new era, and it almost was sort of inevitable that something like Google Earth would develop as a platform for being able to use these images very easily. But that's not what we're going to focus on today. We actually are going to back up here and try and understand, how does this remote sensing work? What is it all about? What are the components of it? How do these things function scientifically? And so in a very simplistic sense, this is what happens. We have a source of electromagnetic radiation energy that's hitting a target, and is being picked up by a sensor that's, in this case, on a satellite orbiting Earth. I mentioned electromagnetic energy, and this is, of course, a key understanding here. The idea that we have what is effectively a flow of energy at the universal speed of light in the form of electric and magnetic fields. And we have these flows occurring at different speeds, at different wavelengths. And we give those, we kind of put them on a big spectrum and give different parts of that spectrum names, including things like visible light. This corresponds to wavelengths that we are able to detect with our own eyes. It's in the 400 to 700 nanometers, or if you prefer, 0.4 to 0.7 microns or micrometers. And it's this range plus kind of the ones next to it, the ultraviolet and the infrared, that are the wavelengths we really need to focus on when it comes to producing satellite images for Earth remote sensing, the sort of images that we're going to see in things like Google Earth, but also some slightly different images that take advantage of the infrared and the ultraviolet, which are things that we can't see with our visible, with our own eyes. There's also sort of some other considerations here. We're not going to dive into this, but just to let you know that it's not simply a case of this full spectrum of EM radiation coming from source, which in our case is primarily the sun. Also sort of some wider sources in space, but mostly the sun hitting the Earth, being reflected off, because it's not that simple. First of all, not all light is reflected by Earth. Some of it is absorbed, and then some of that is later re-emitted. And a big reason for that is because we've got this atmosphere in the way. And the atmosphere, it's very important for us to survive because it actually protects us against some of this radiation which would do us harm, and it doesn't let it through. It just absorbs it or reflects it. And so there's only certain wavelengths that are let through. Now, we call these sort of gaps where they can come through atmospheric windows. And a big one of these is for the visible range, which is fortunate and also sort of logical, really, of obviously the stuff that can get through corresponds to the light that we've evolved to be able to see with our eyes. So to go back to our simple diagram, we have this EM radiation coming in, it hits the Earth. As I say, some is reflected, some is later re-emitted after being absorbed. And that radiation can be detected by a sensor, or sensors that are sitting on satellites orbiting around the Earth. Once the sensors have collected this information, at some point it is transmitted down to the ground. It's basically encoded as a bunch of zeros and ones, digital information that's picked up by a satellite dish, a receiving unit. That sends it then to a processor that looks at that information and interprets that information, and then feeds it into some sort of application that's able to give us a representation of it, probably an image, because that makes most sense. So what are these images? Well, an image, a digital image like this, is really just a bunch of numbers, where each of these numbers represents a square or a box. And the higher the number, the whiter or the brighter that box becomes. So for 0, we would have a black box. For white, we would have 255. It's a binary scale we're using. Oh, sorry, it's a magnitude 2 scale that we're using here. So we number these boxes and they're colored according on this sort of gray scale. And we call these boxes in the image pixels. And when we put all these pixels together, all these numbers together, we start to get these shades of patterns and shapes, which then if we just take those numbers away, we end up with something like this. We end up with an image. In this case, it's grayscale, because we're talking about numbering each of these pixels or coloring each of these pixels on a scale from white to black. But it clearly creates something that we're able to recognize as stuff we know. You know, we can recognize the shapes here. For example, if you were to show this image to pretty much any Australian, they would immediately identify it as a sports oval. In fact, if they lived in Melbourne, they would probably immediately tell you that this is the MCG, the Melbourne Cricket Ground. And this is just in black and white. If we add color into the mix, it becomes even more obvious what we're looking at. But the thing about, if we go back, sorry, the thing about this is, you know, some people might not have seen an oval of a cricket ground before. And so it might not be obvious to them what they're looking at. Or if we ignore the cricket ground, it might not be obvious what these sort of darker green splotches are that seem randomly distributed around, or in some places maybe seem to be in lines. Well, I think most of us can realize they're trees, even if we don't really know how to interpret satellite images, if it's not something we're familiar and looking at. And the reason for this is our brain is very good at recognizing textual and geometric data, basically patterns and shapes. And it's particularly good at doing this if we have contextual information, i.e. if we have some sort of background information and understanding of what we should be looking at. So to illustrate this, let's go to some images that we've introduced in previous seminars. These are the street view, the 360 images that we collected at campuses of the partner schools in PNG and are now available on Google Maps and Google Earth as part of the street view layer. And so we're looking at an example sort of in one direction of the 360 image on the one side of the screen there, and we're looking at the corresponding satellite image. Now, I was the person that uploaded these images to Street View, and in order to do so, I had to geolocate them. I had to find exactly where they were, but I didn't have that information. And I've never been to these campuses in PNG. So I had to rely on the satellite images in Google Earth to try and find where they're located. And so to do that, I had to explore around the images and I had to try and correlate what I was seeing on the ground-based view to what I was seeing in the satellite view. And sometimes this is really easy. For example, here we've got this bright red roof, shows up vibrantly in the satellite image, and we can see it in the street view in the 360 image too. And so it's clear that we have to be looking at that building. And if we just sort of think about the shape of the roof and the shape of the building in front, we can quickly understand that it's off here to sort of the northeast of that red building. Now, sometimes, you know, we don't have quite the right angle of view of the shapes that help us. What I mean by that is if we look at the satellite view, which is now on the left side, or the opposite side from last time, we have these round shapes. And if we look over in the 360 image, we see these what are clearly water barrels here, which hopefully we know or can tell have rounded tops. We can't see it from this angle, but we can see that these these green containers must be the containers over there. Now here we have 4 containers, one sort of hidden at the back. In the satellite image, we have 8, or sorry, we have 10. But this is another thing we've got to bear in mind, that these images were captured at different times, and so things may have changed. But again, your brain is very good at sort of piecing together the information here and seeing that, you know, despite this is clearly what we're looking at by correlating to the other buildings around and the earth underneath, and even where we see patches of grass versus bare earth. Now to look at one more of these, you know, sometimes it gets really hard. Sometimes you just have a bunch of buildings and maybe some landscape fields or topography. And so you have to kind of take a wider view and try and see, okay, how does the topography line up? How do the trees and the fields, you know, is there any information in here that can really help us? And so actually those 3 stripes, the black stripes on the roof were the real key information at the end of the day. A lot of it seemed to fit, but there were different places where this could have been. But those 3 stripes made it clear that we were in front of this building that was towards the top of our satellite image here. So, understanding shapes of images is clearly important. You know, you could say, well, okay, you were just sort of zooming out and looking at stuff there. Why don't you just get closer and closer to your image and you'll get more information? It'll be easier to see the detail. Well, that's true, but only to a certain extent, because there's a limit to how much detail we can see in these images. Remember, they're made up of these boxes, these pixels. And the size of those pixels, what we call the spatial resolution of those pixels, depends on certain things. So when I say spatial resolution, I mean what one pixel that you see on your screen actually represents in the real life, like what distance. And that distance can be radically different depending on what sort of data and what type of satellite we used to detect that information. And a key part of understanding what a satellite can give us is, first of all, considering what orbit it is around Earth. Now, one way to put satellites in orbit is in something called low Earth orbit, which that sounds good, right? Low Earth, close to the target, then surely we're going to get better information, higher resolution information. Well, that is true. That is definitely true, but there are also some trade-offs we're going to look at in a minute. Now, sometimes we instead of just putting in some random low Earth orbit, we might put it in a polar orbit. That has certain benefits in terms of repeat coverage, what we call the temporal resolution, how frequently we can recapture the same area. Depending on, so that has benefits depending on where we want to look at. There's also something called a sun synchronous orbit. The advantage of that is we're sort of in lockstep with illumination from the sun, which means whenever we pass over a certain place, the sun angle should always pretty much be the same. So we're not getting these changing shadows on our image, and that just makes interpretation of change a lot easier. Hopefully you're picking up on the idea here that the important thing with satellite remote sensing and images is that we don't just do it once, that we keep capturing it, because change of landscape is kind of, that's the key thing. That shows us what's going on in the planet. With that said, you know, sometimes we might just want to hover over one point on the planet. There are reasons for this. There's a reason, and we call this geosynchronous. Basically, the satellite rotates in lockstep with the rotation of the planet. You know, reasons for this are things like communication satellites that want to know that we're in a set place so we can bounce the signal off. Reasons for it in a sort of Earth observing fashion are things like weather satellites, when we want to just keep looking at maybe a whole hemisphere of the Earth and seeing how the weather patterns in the cloud changes. But let's go back to that low Earth orbit. I mentioned that there are trade-offs between this spatial resolution and what I call the temporal resolution, because if I'm in a low Earth orbit, it's clearly going to take me longer to get all the way back around and recapture that same image, as opposed to if I'm in one of these big far out geostationary orbits, which are 36,000 kilometers away from Earth, as opposed to a few hundred kilometers where you have low Earth orbits. There we can basically sit there and just repeatedly take pictures. They're going to be high resolution, but because we're so far away, they're going to be high temporal resolution, but low spatial resolution. They also, when we're far out, they have what we call a large swath, as in there's a large area in the field of view, as opposed to our low Earth orbit, where we're only going to get small swaths. So yes, we get this really high spatial resolution, but repeating it and capturing it is quite an arduous process, because we can't do that rapidly or over a large area. There are some other resolutions that you might hear about. We're not going to delve into this too much, but there's something called spectral resolution, which basically refers to the ability to measure certain electromagnetic wavelengths. When you have sensors on satellites, you might think that it's logical to just, hey, collect everything, all wavelengths as much as possible. But you know what? That actually isn't too helpful for a number of reasons. First of all, we mentioned how some wavelengths are just blocked by the atmosphere. So having a sensor detecting that is kind of a waste of space, and putting things up into orbit is expensive and difficult. So, you know, you don't want to take away your valuable cargo weight limits. So you want to really focus your sensors on specific wavelengths, also because these specific wavelengths relate to certain things that we might want to detect, certain types of gases in the atmosphere, stuff like that. So really, this is about kind of fine-tuning our detection. Similarly, we have radiometric resolution, where we're able to discriminate finer differences between the energy that's reflected or emitted, basically more sensitive sensors. And again, you know, the more sensitive something is, that can have pros and cons. You know, it can be a little harder to make it work. It means we have to collect more if we're only collecting in a, if we say we're only collecting in a very narrow wavelength, then we're going to want good radiometric resolution so we can collect lots of the radiation and get a good strong signal. So we've collected this information, and as we've seen, we can make it through the use of pixels into an image. But so far, the images we've looked at have been what we call panchromatic, basically grayscale. But as we know, you know, the world isn't in grayscale. There are colors corresponding to different parts of the visible spectrum. And even we humans can detect this with the rods and cones that are in our eye. They're able to pick up on key colors, primary colors of light, detect amounts of red, amounts of green, amounts of blue. And they're able to combine these together to form other colors. Now, remember, we're talking about light here. So if you're a painter and you're used to mixing paints and you're like, hang on, those are not the primary colors. It's not green, it should be yellow. Well, that is true for paints. And that's to do with the way light is reflected and emitted by pigments. But we're focusing on mixing light here. So our primary colors are RGB, red, green, blue. So let's imagine we have a satellite that collects a bunch of red light. a bunch of green light and a bunch of blue light from a target, and it places them into a, quote, red channel, green channel, blue channel. If we then combine those three images together, we get what's called a true color composite. It's a sort of, image that looks the way that it would look if we were up staring down at the planets. But you know what? There's no reason why the red light has to go through the red channel and the green through the green channel and the blue through the blue channel. These things, or the blue channels we put here, sorry, there's an L seems to have gone missing. We could put the blue through the red channel. I know that seems really counterintuitive, but also we don't even have to necessarily just focus on red, green, and blue light. Whilst our eyes can only detect in the visible range, sensors on satellites, as we mentioned right near the beginning, can detect in things like the infrared or the UV or whatever we basically make them work in. And we can take that data and we could, for example, detect in the near infrared, and we could put that through the red channel. And now let's make the red the green channel and the green the blue channel, hopefully the blue channel at some point. And then we combine that red, green, and blue RGB into a composite image, and it gives us what's called a false color images. And here we see the two compared. On one side, we have the true color, on the other side of the false color. And you might say, well, why do that? It's just the same thing, but it looks weird. Well, because we're trying to extract information and understanding from the image. Say, for example, we wanted to map areas of vegetation. Now, in the true color image, you could say, well, okay, it's just going to be where there's like trees and fields. But what if those fields were fallow? What if they were bare earth? What if they only had sort of like, dead vegetation in there? We might struggle to discriminate. So by combining the infrared, the red and the green, we actually create an image like we see on the other side here, whereby the vegetation shows up in red, and sort of bare earth or bare urban environments, roads, houses, all show up in these bluey colors. And this occurs because healthy vegetation reflects very strongly in the near infrared. So we are highlighting that through the infrared channel that or through the red channel that we put the infrared information into. And this is, again, going back to something I mentioned a bit earlier, this is the key and the reason that we use satellite images. It's to give us more information than we can find by just looking for ourselves. Like if we just wanted to like look at where there's vegetation, we could easily just fly a plane over and take pictures. Or we could just go there ourselves maybe. Except we can't always go there ourselves. Sometimes places are remote. Also, if we want to see repeatability, we can't keep going there. So this is where satellite images really come to the fore by giving us repeat coverage of the same area, giving us information in bands, in wavelengths that are not easily detectable by our eyes or even by just sort of a simple photograph. We can gain an amazing understanding of the landscape of the planet. And that's something that's has been important. And I feel it's going to be ever more important as we enter this future where we see the impact of global climate change and of rising population and the stresses that places on agriculture and water resources and climate change affecting weather patterns, and all of these things. If we want to, as a species, kind of get beyond this and thrive despite some of these challenges, we need to understand the world we live on. We need to understand what it looks like, so maybe we can do a better job of taking care of it. That's what interests me as a scientist. That's why I like looking at the landscape. and trying to use satellite images to understand the world. And I'm hoping through the seminars we've presented, you'll use tools like Google Earth and use satellite images to do the same. So that's all we have for you. I appreciate you spending time with us, either in this seminar or previous seminars. Thank you, thank you. If you have questions and want to reach me, please reach out to the PAST team, or you can track me down via my website, northisdown.com. Thank you.